Hi, welcome to Coding Architecture 1. In this video, we are presenting the roadmap of becoming a computational designer, as mentioned previously, in which we're trying to give you an overview of all of the concepts that you should learn in order to become a computational designer. This will include things that are not in the scope of this semester, but the purpose of this roadmap is to give you a good overview of where you are in the learning process and why you're learning the things that you're learning as we move along. By the end of the semester, you should be able to check off a good number of items from this roadmap and have a good feel of how far you've come in this time. So let's dig in. The roadmap is based on the definition that was presented on the first lecture, the definition of software as data structures plus algorithms equals programs, which is a definition by a Swiss computer scientist called Niklas Wirth, who was also an ETH professor back in the days, and it's also renowned by creating many famous programming languages. So let's get started. The roadmap is read from left to right, very much like a grasshopper definition. And it starts actually by describing how does a program run. And it highlights in green how the things work in Grasshopper, and in blue how the same concept is in Python. So here we see that like the first difference that we see is that a Grasshopper program, like a visual program, is run from left to right following the wiring, while a Python program is run from top to bottom, line by line. The next concept is that of the building blocks that I went through some detail in the first lecture, but I will again dig into it because it's quite important. So the first among the building blocks, the first important building block that is worth mentioning is the non-executable blocks, things that are just comments. In Grasshopper, you do this with a scribble component, and in Python, you do this with comments. You have multi-line comments and single-line comments, which are prefixed with a hash. I'm going to switch also to a Grasshopper file that contains many of these examples. This Grasshopper file, Grasshopper definition will be available as well in Moodle. So here we see side by side again, green is Grasshopper, blue is Python, and this is a Grasshopper comment, basically using the scribble component, and this is a Python comment with a hash at the beginning of the line. Now, going into actual code that executes, the first element, the most basic unit, you could say, of a program is data, a data value, which basically exists first on its own. Data can be of different types. It can be single values, or it can be multiple values. It can be a mapping between different values, and so on and so forth. We will dig into the different data types later on, but for now, the concept of one or many is what is relevant. Also, something to highlight here is that data types are not just about categorizing data, but also about determining which operations we can perform on that data, because we cannot multiply two strings, two pieces of text meaningfully, or we will have multiple parts of text, but it's not the same operation as multiplying two integers or two numbers in general. Once we have data covered, and we will see that actually data extends quite a bit later on into what types of data we can build. we move into the part of defining the algorithms. Basically, how does each of the platforms allow us to encode algorithmic logic? So the first is inputs and variables. These are like it's like assigning a name to a piece of data. Here we had a piece of data that was living on its own, but we want to give it a label or name. So on Grasshopper, we put it into an input parameter, for example, and on Python, we would put it into a variable. If I switch back to the Grasshopper here, we see that like data living on its own is just data, exactly like this in Python, just data. It's not assigned to variables. It has no name, nothing. But once we feed it, for example, into one of the input components, it will have the name X. Or if we assign the results of some operation to a variable like this, it will have the name highlighted here. So variable provides a name for a piece of data. Now, data, like data values and variables, and a few more things like operators, can be combined into what is called an expression. An expression in Python is something that returns a value. It has a value that is provided, like applying an arithmetic operation like this, plus 42 plus 10 is an expression that produces the number 52. Now, expressions return the value, but if we're not doing anything with them, the value is lost. We can print it immediately, and printing an expression is a statement. A statement is the next unit of composition. So we have data on one hand. Data can be put into variables, and data can be combined with operators, and all these three things can be combined into expressions. Expressions can be composed by, can be combined into one larger unit called statements. And statements perform an action. So they have some kind of side effect, like printing an expression has the side effect of actually showing something on the screen. We will see that there are different kinds of statements. Some of them are very important, like conditionals, iterations, and then assignment is a statement. So in the case here that we assign an expression 42 plus 10 to a variable, that is a statement. In Grasshopper, the equivalent would be, for example, if we use the addition component, and we have two inputs, A and B, and that results in some result, and we can use a name relay or a data component in this case to give it a label to this variable. In this other case, for example, we don't name it, so it has an output name, but then the name is lost in the wiring. Okay, continuing. Statements can be composed into larger units even, which are basically used to create algorithms, because algorithms are step-by-step procedures to solve some kind of problem. As we've seen earlier on, there are very simple algorithms, like creating the absolute value algorithm is simple enough that it fits on like only 4 lines of code, and it uses a conditional statement. We check if a value is less than 0, and if it is, then we use a statement to print that value, but multiplied by -1 in order to make it positive. If not, else. would print the value as it is. This would be the implementation in Python. The implementation on Grasshopper is a bit more convoluted. Grasshopper is not really kind of very well suited for this sort of if then else kind of behaviors, but it's still possible to implement. Now, like the next layer, the next building block that we can use is aggregating, making these algorithms reusable into functions. If we wrap an algorithm in a function, we can reuse it later on. And there are functions, we will see there are built-in functions that are coming with Python, and we can define our own like user-defined functions whenever we want. Now, in terms of Grasshopper mapping, all of these things, from operators to algorithms, are somehow grouped into the components, Grasshopper components. There's no different degrees of granularity in here. And finally, the last building block that we're going to see is classes. A class is a way that we have to bundle data and behavior algorithms into one cohesive object. Say, for example, that you want to create you want to create something like a brick, for instance, and you will make use of that brick. You will create many instances of that brick in your code. The brick has data, obviously, that's kind of intuitive to say, okay, a brick has a length and a width and a depth, for example, but also has behavior, has methods that belong clearly to that instance of that object. For example, we could say calculate the weight of a brick, because we know average density of a brick. So we can say that width, taking into account the width, height, and depth of that specific instance of a brick, we can calculate the weight of it. Classes are very useful. We will actually notice that we use them all the time. They exist. All of the objects that we use in Python, they are built with classes. And we will see how do we create our own later on. In Grasshopper, this is not exactly the same. We can have clusters somehow as a way of creating reusable building blocks. Hops is also something that goes into the same direction for newer versions of Grasshopper. Okay, that ends what we will see in terms of algorithms, how much we can kind of grow into units of defining algorithms. What comes after is how do we organize our code? So all of these things will have to go into files. In Grasshopper, this is a Grasshopper definition. That's pretty simple. That's the only thing that we have. In Python, we have different levels of granularity. We have modules. A module is simply a Python file, a file with a .py extension, and can contain classes and functions and whatnot. A package is also very simple. It's just one folder that contains multiple modules, or multiple Python files, and has an init file just for clarity. And then a library is nothing more but an aggregation of multiple modules put together. We will see how these things come to place, but we don't need to worry about this stuff much. We will only use modules a lot, so we will not create many modules at the beginning. Okay, the next stage of the roadmap is coding essentials. These are the things that you really need to grasp relatively quickly. We've seen them in the first lecture. We will see them in the second and the third lecture very much in depth, and please reach out if some things are not clear. We will try to see and provide some more exercises for these things. So first thing is data types. As mentioned, there are four primary data types, let's say integers, numbers, or floating point numbers, text, which in Python is called strings, and booleans, which are true or false. Then there is the concept of nullity, or in Python this is called none, which is a variable that could contain something, but at the current time it contains nothing. So this is called none in Python, and Grasshopper refers to this as null instead. We have seen operators a bit, arithmetic operators. This was also in the ungraded assignment. Then comparison operators. We briefly touched upon this. Is here we're using the comparison like less than. There's a Grasshopper file in the first week that contains all of the comparison operators. There's also like a pretty close one-to-one match to Grasshopper in terms of comparison operators. Then there are logical operators in Grasshopper called logical gates, which are basically the keywords and, or, and not. So these allow you to combine different conditions. So if result equals 2 and result 2 equals 5, for example, or you could say if result equals 1 or result equals 3, then do something. Or you might want to say if not result 5 equals 5, and so everything else but 5 would be 8. These are all logical operators. There are examples again in the Grasshopper. Then there are built-in functions. Python has plenty of them. There are also some commonalities or some equivalences to Grasshopper. There's the panel is kind of a print. There's a sum function that is kind of like a math addition in Grasshopper. Getting max and min, these are two built-in functions. In Grasshopper, you could do that with bounds plus a deconstruct domain a component. Operating on lists, like operations that work on lists, getting the length of a list, len is a built-in function, which you would do with the list len component in Grasshopper. Sorting a list with the function sorted, and there's also sort. We will see the difference between the two later. In Grasshopper, that's the sort list. And range, to generate a series of numbers in Grasshopper would be series, or also there is a range. One thing to highlight here is that Python is very much self-introspectable. You have these built-in functions like help, dir, and type. Dir of something will give you all the methods and all the attributes of that something, that object, whatever that is. Type will give you the type of whatever you're testing. So if I open a Grasshopper component and I say a equals to 42, I can also print type of a, which is a variable, and it will tell me that it's an integer. I can also ask help on things. Let's say I don't remember what type was doing. There's a help function, but if I call it without anything, it will not do much. So if I say help type, but if I print what help does, you can also put it into a panel. It will print the help on the thing that you put in here. So this is the type, like well, this is like the definition of what type can do. And every object in Python is introspective in that sense. You can always say help of help. You can even say help of help itself. which is help on the built-in function help. Help receives an object and returns text. Okay. Moving on, we will see user-defined functions. We will go to data type, iterable data types. This will be in this week's lecture. We will see lists and sets and nested lists and data trees, which are the equivalent in Grasshopper. Tuples as well. And one, or actually 4 little things that I want to mention about extensions. In Python, everything is an object. Absolutely everything is an object. An integer is an object. An instance of a class is an object. Function is an object. A module is an object. Everything at all is an object. That means that everything has some kind of properties attached to it. And that goes to the next one. Everything is inspectable. You can get the reference of anything and inspect it and see for a number what are the operations that are available in that number, what is the data that is available in that number, and so on. The third one is a bit of a reference to the aesthetics of code. Is this sentence beautiful is better than ugly? This comes from something called the Zen of Python, which is a list of 19 aphorisms somehow, of which only it's a list of 20 aphorisms, of which only 19 are actually written out, and then 20th is left to the imagination of the user. It's available online. Funny enough, this is also available to type something very special in Python. To say import this and test, they will be printed on the screen. So that's the Zen of Python. And then last but not least, indentation matters. Python is a language that is very sensitive to white space. So everything is inside blocks, and you'll see that screwing up the indentation screws up your code. Okay, we move to control flow. Control flow is how we will define algorithms, basically. Statements that have some kind of, perform some kind of action that will branch out the code or iterate the code. The main 3 ones that we will see is a conditional statement. If this, then do that thing. If has 2 other parts. It has an elif, which is another another condition. So you can check if condition 1, elif condition 2, elif condition 3, elif condition 4, and so on. And then if no condition is matched, but you still want to do something else, then you say else. We will see this later on. Iteration statements, the for loop is the iteration statement. We say for if we assume that we have a list of numbers, and here I'm creating a list of numbers that have no relation, then if I want to print them all, if I print B, I'm going to print the whole list with the square brackets included. But if I want to print one by one, I can say for I, for example, or item in the list B, then for each of them, do something. And what I want to do is print B, print item. So now if I test, this will print one by one, line by line, all of the items in the list. For statements, or iteration statements are very useful. We will use them all the time. And here it's important to highlight one thing. Grasshopper doesn't have the same thing, although it has something that matches very closely, which is implicit cycles. If you plug multiple items into a component, that component will run n times, one per item that you plug into it. That is, unless you say that the input is set to be of list access. So in that case, and we can test this here. If I have print of x, for example, and I have only one x, if I add a second one with shift, now I have an implicit cycle, and this thing runs twice. And if I add another one, it will run 3 times. But if I now change this to list access, from item access to list access, what I get now is the other behavior, the one that was printing the whole list, because now X is the entire list. Okay. Then the last control flow statement that we will see is the while loop, which is useful to create repetitions until a condition is given. While loop, considering the way that Grasshopper behaves, is a bit problematic sometimes, because if you enter the wrong condition, you might end up in an infinite loop, which will freeze your Grasshopper, and then you lose data if you didn't save it. Okay, moving on, after that, we will start going into geometric data types, primitives, data structures. We will go deeper into data structures later on, and solid geometry. After that, some concepts of advanced coding. We will see dictionaries quite a bit in depth later on. We will focus a lot on classes, object-oriented programming. We will see that it's actually that we are using it all the time, even if we don't realize. And then we will create some classes of our own, which is very simple. We'll see some code organization details, but not a lot. This is where the course will sort of stop conceptually. We will see some of the things that come after, but not that many. For example, advanced concepts of functions and so on, iterators, lambdas, recursion. We will not see many of these things. We list some of them so that you know that they are there, but we will not focus on them. We will also not see handling input-outputs, serialization, files, networking. This is all coding architecture 2. And then an interesting outlook into like broadening your perspective is a set of well-known algorithms. We start first by basic paradigms of algorithms, like divide and conquer, backtracking, brute force search. Things are like fundamental approaches to how you solve a problem. And then some categories, classic algorithm categories, like sorting is the mother of all algorithms. You usually start by sorting stuff before you do anything else. This is kind of almost a given for a good number of algorithms out there. Searching, there's many searching algorithms. Graph traversal algorithms, weighted graphs, combinatorial search, optimization. There's a lot of things. And we might mention some of the algorithms in computational geometry, triangulations, bin packing, convex hull, you might know already, Boolean operations, and so on. And here, well, there's this note about the big O notation that we might see at some point later on. And then this branches out into further specialization, like you can go into robotic fabrication, 3D printing, structural design, so on and so forth. In coding architecture 2, we will focus a bit more on the robotic fabrication and the transition to machines. With that, we're done with the overview of the roadmap. We will post this roadmap and the video on Moodle. So I hope to see you all soon. Thank you very much.